very much for the opportunity to talk here. I'm excited to be giving my first talk. I'm going to discuss the size dependence of CO dissociation on cobalt nanoparticles. And so these cobalt nanoparticles are interesting for Fischer-Tropsch synthesis, and I'll first start with a discussion of what Fischer-Tropsch synthesis is, and then talk about the tools we use at the ALS to study this reaction and nanoparticles. And then I'll present the results about the CO adsorption and dissociation, and then the outlook of the research. So Fischer-Tropsch synthesis is a reaction to go from carbon monoxide and hydrogen, which is called the syngas mixture, into hydrocarbon products. And it's a way to transform cheap and abundantly available raw carbon sources such as coal or biomass and turn it into liquid fuel products which are more useful. Excellent. Yeah, so the pros of this process are that you can produce very pure liquid fuels with very low sulfur content and aromatics content, and you can make use of carbon reserves that are not currently being used to their full potential. The cons are that you can put basically any mixture of carbon monoxide and hydrogen in, and you get a slew of products out. It's not a very selective reaction. So if you can improve the selectivity or understand the fundamental mechanism of the reaction better, then you can make this a more financially viable option compared to traditional fossil fuels. And talking about financially viable options, that's the next slide. But first talking about the mechanism of the reaction. I mentioned that one of the fundamental shortcomings is that we don't have a good understanding of the mechanism. And there's two sort of competing ideas about what goes on in the surface of a metal. They differ mostly by what happens to the CO when it adsorbs on the metals. So in this first theme, we have CO comes into adsorbs on the surface and then dissociates into molecular oxygen and carbon. In the second type of reaction scheme, it just stays molecularly adsorbed on the surface. Typically today, it's thought that this reaction mechanism tends to dominate, especially in the production of alkane products. But the CO insertion mechanism might be important for the formation of oxygenated products. And you can maybe see that in a step where you have an intermediate like this, it might not fully reduce, and you might get a ketone or an alcohol end product there. So now I'll talk about the Fischer-Tropsch metals. One of the biggest considerations is picking which material system to work with. There's pros and cons to different Fischer-Tropsch metals. Iron is typically the most used in industry because it's the cheapest. But we can see that the cobalt has a slightly higher chain growth probability, so it might help favor higher molecular weight products, which could be useful. So the choice of metal helps affect the selectivity of the reaction, but also it is a trade-off between the longevity of the catalyst and the activity. So this is a theoretical volcano plot that was calculated by the Norskov group, and it shows the activity of different Fischer-Tropsch metals. The center of the volcano is sort of the optimum, where the products will desorb at an appropriate rate, but the production of methane is high. And you can see that cobalt is closer to the center of this volcano than iron is. And even closer is ruthenium, but ruthenium is prohibitively expensive, so we didn't go down that route. So choosing a metal is really a question of time versus money. With the cobalt-based catalyst, you might be able to get a more long-lived catalyst because it will be more resistant to coking and deactivation over time. But with an iron catalyst, you have a cheaper starting material, so maybe you can just dispose of it when it gets crummy. So we're focusing on cobalt because we think we can improve that and get full use of this optimum performance. So the sample preparation that we do is we look at monodispersed cobalt nanoparticles so that we can study a size effect of them and understand some of the fundamental interplay between the gas molecules and the catalyst, and maybe use size to tune the selectivity or understand the difference of reaction on different sizes. Then we disperse the particles on a gold substrate, and it's important that the substrate is inert to the reaction. If you go back to the volcano plot, you see that gold is way up in the corner, so it doesn't interfere with the reaction so much. And it's also important that it's a conductive substrate for when we do the X-ray experiments so that we don't get charging, and that we can collect a total electron yield signal. It's also important that the cobalt is well dispersed on the gold because you don't want the particles to be too closely clustered together, because then they might sinter and destroy the catalyst over the course of the reaction. But you want it to be dense enough that you get a good signal on the sample. So this is a simplified schematic of our gas cell that was designed in our group. We have some key features here, that there's a gas atmosphere around the sample. So we're doing an in situ measurement of the surface species. And we have a silicon nitride membrane that's about 100 nanometers thick to separate the CUHV environment out here from the sample chamber. And there's an infrared laser to heat the sample to the reaction temperature. And this is kind of a nice feature because it allows you to collect a total electron yield without the interference of a resistive heater, which has high currents and can cause inductively coupled currents to flow in your sample. So the IR laser is nice for that, and it also helps to localize the heating in the gas cell so you don't heat up the walls of the reactor and melt the O-rings that are there. That would be bad. So, and then we have gas in and gas out, and we control that by a set of mass flow controllers outside. Then we measure the total electron yield signal, which is the replacement current, into the sample as the photoelectrons are emitted from it. So some pictures of the actual gas cell. Here's the silicon nitride membrane. Here's the sample cavity, and the sample is placed here. There's a wire feeding through to collect the total electron yield signal, and another wire to measure the thermocouple for measuring the temperature. And here you can see that there's O-rings to seal the cavity. A couple issues with this design are we're dosing a toxic gas, and we want to make sure that it's going to perform safely. Thank you, Doug, for checking that our experiments are safe at the ALS. So one way we treat this problem is by doing a leak test in the situation. So we connect all of the gas lines together, pump them to vacuum, and then turn off the pump and see what the leak rate into the the system is. And we set a threshold that 3 torr in 3 minutes is an acceptable leak rate. And another concern is the infrared laser, but in this design, we embed the laser in this cavity, and it hits the back of the sample, so none of the laser light is reflected out of this closed cavity. So it minimizes the hazard there. So the experiment that we perform is first to pre-treat the catalyst. We oxidize it at a high temperature to burn off any ligands that remain from the synthesis process. Then we reduce it in hydrogen to return the catalyst to a metallic state for the reaction. Then we look at the adsorption behavior in carbon monoxide, and then we react away the carbon monoxide with hydrogen to see what products form and at what rate. In this talk, I'm just going to focus on this adsorption step. So I had some questions about this at the poster session, is how can you measure an X-ray absorption spectrum in a gas atmosphere? And now I can go into a little more detail about the intricacies of that. So these are graphs showing carbon monoxide and helium in different ratios in the cell, and looking at the oxygen K edge on 10 nanometer particles. And we see that there's these weird double peaks where we should see the CO adsorption. And we think that this is actually because of the gas phase. So if you increase the concentration of CO in the gas phase, this peak actually becomes deeper, and it's actually not a peak, it's a valley. So the gas phase is actually screening out some of the flux that would be in this region. So to overcome this problem, we treat the particles with 1 atmosphere of gas at an elevated temperature, and then we replace the gas with helium so that there's no gas phase contribution to the spectrum, and we're only focused on the surface of the particles. So we get a much cleaner spectrum on the oxygen K edge when we pump out the, well, not pump out, replace the CO with helium. So this shows the size dependence of the nanoparticle and the CO adsorption. We have 2 spectra at different temperature on the small nanoparticles, 4 nanometers in diameter. And we see a nice peak from the molecular CO adsorption on the oxygen spectrum. And on the cobalt spectrum, even at elevated temperature, we see that the CO does not cause oxidation of the cobalt. It's in its reduced metallic form. So this is a good indication that the carbon monoxide is not splitting into its atomic components. In larger particles, we have a cobalt oxide peak that's starting to form, and that forms even at room temperature. And in even larger particles, we have a bigger contribution from that peak. That corresponds to oxide features that form in the cobalt L-edge spectrum as well. So these two together are good evidence that we're forming surface oxide species because of CO dissociation. If we look at the ratio of the 2 different types of adsorbed CO peaks with temperature and size, you see that there's not a temperature dependence on the 4 nanometers because the CO doesn't dissociate in the first place. And then with elevating the temperature at the 10 nanometer size, you get more dissociation at higher temperature and even more with 15 nanometers. And so this shows that it's a thermally activated process. So others have observed size effects due to cobalt nanoparticle catalysts as well. These show the turnover frequency for methane production as a function of size. So what others have found is that small nanoparticles are not as effective at producing methane, which is the end stage of what we're trying to study with were just studying the first step, and now they're also showing that the final step is worse. In this plot, it's plotted as a function of surface cobalt, and here it's plotted as a function of the weight of cobalt, so the entire bulk of cobalt. And so this fits really nicely with our result that we see less dissociation on the smaller nanoparticles. So this is a good indication that the CO dissociation is an important first step for this reaction to occur. So the question is, why is the CO dissociation worse on the smaller nanoparticles? We wanted to answer the question of why is the methane production worse, and now we've answered it with why is the CO dissociation worse. Some ideas about this are that the small nanoparticles don't have enough surface sites that the CO can absorb on and dissociate on. It has a lot of very highly defective sites because it's a very small surface, but not the appropriately coordinated sites. And we think that hydrogen chemisorption also plays a role. So the small nanoparticles are not as effective at dissociating hydrogen, which helps dissociate the CO, and it's a chain reaction in that way. And next, we'd like to study how the selectivity can be manipulated by alloying the cobalt particles with other metals and seeing if we can favor oxygenated products or select for a certain group of products. And then we want to study if CO can be used as a reactant. And in summary about this study, we found that smaller nanoparticles are not necessarily better. One would think that smaller nanoparticles are better because they have a high surface area to volume ratio and you can make better use of the volume of material, but actually the catalytic activity goes away as you get too small. So there's an optimum size around 5 to 10 nanometers. And in cobalt, dissociation is an important factor in determining the catalytic performance. I'd like to acknowledge my team members on this project, especially the postdocs who helped train me and taught me a lot of the techniques that were involved with the synchrotron work and the cobalt synthesis, and also the folks at the ALS who've been very helpful to interpret and collect the data. Thank you.
So I was reminded, since we are streaming live, we should have microphones for questions as well. Do we have any questions for this talk?
First of all, it's a wonderful talk. So I was wondering that the cobalt is a wonderful material if you look at that volcanic part. But next to it was also bimetallic system like iron, nickel.
Yeah.
And the price of cobalt, I just checked, it is about $14 per pound. It's still expensive.
Yes.
So what would you do?
So we're trying to look at bimetallic systems also as an alternative solution to the problem. And if you can get a selectivity improvement, that could be worth the extra cost because that means you have to go through less subsequent processing steps in a plant. So it could be a significant trade-off.
Additional questions?
So, Mahati, a very nice talk. One problem maybe with the measurement right now is that you have to remove the CO to measure the cobalt, right?
Yeah.
And I guess you would like to keep the CO there because you may change what's the concentration of surface species once
Yes.
you remove the CO. So do you think you can come up with a clever scheme to subtract the gas phase out of your spectra, of the oxygen spectra, right? It's not a
Well,
problem for the cobalt
We
always.
could measure the gas phase and then just subtract
Right.
it from the spectrum, but we don't... Go away. We don't think that that's as much of an issue as one would think because we measure over time the CO adsorption peak and in just helium, and it doesn't decay. So it's staying adsorbed. It's not suddenly.
Well, you may have a steady state after initial loss, maybe.
Yeah, that's a possibility.
Okay.
More questions?
So I guess implicit in the interest in nanoparticles is that they have a high surface area compared to, well, a flat surface. But what is can you comment on the relative effectiveness of just a flat cobalt surface compared to the nanoparticles?
A flat surface starts to behave more. Oh, go away. Starts to behave more like this 25 nanometer point in this study, so you don't really gain a lot more activity after a certain point, and it starts to become less advantageous to use a bulk because you don't get as much surface area.
I just wanted to point out that, of course, that once you're going between that, few nanometers up through 10 or 15 nanometers, it's not just the perfection and the surface volume ratio. Your crystalline structure does change. Since down to the 5 nanometer, you're definitely down in the range where you have special orientation or special arrangements of the atoms based on the finite size effects.
Other questions? Just going to make me run around.
So, to me, one of the most interesting topics you brought up was these two possible mechanisms of CO dissociating into atoms or CO inserting into a carbon chain that's already there. Do you have any ideas for experiments that might come next that could help you differentiate between which of those two mechanisms is really happening?
Well, we think that this experiment helps show that the CO dissociation is happening, but maybe we could pre-adsorb methane on the surface and see if it still grows. If you produce oxygenated products, that would be a good indication of the second mechanism.
Any more questions? Come on, she's tough. She can take it. There we go.
So you have an IR laser which you're not tuning. You can think about having a tunable IR laser and then basically exciting particular modes in your hydrocarbons and really going for mode selective sort of, reactivity. Have you thought about that?
I haven't really thought about that. We're shining the laser on the back of gold foil, so we're not shining it on top of the particles. Well, then it would be hard to shine the X-rays on top of it. But that's an interesting idea.
Any more questions?